Hello and welcome friends. Today we'll be discussing another technique for designing algorithms for certain computational problems. Now the technique today is similar to the technique that we have discussed in our earlier classes, which is backtracking, and the technique today that we'll be discussing is known as branch and bound. So we'll see how this branch and bound differs from backtracking and if there are any similarities. So if you look at the screen, the branch and bound technique is basically you can say it's a method that searches the state space tree using any search mechanism in which the children of currently active node are generated before any other node becomes active. So you might remember in backtracking that whenever a node becomes active, we test whether this node can be expanded, and if it is feasible, if we can expand, and we generate one of its children, and then the child, if it is again feasible, becomes an active node. Now its parent, although has not yet been completely kind of expanded, all its children have not been generated. So it is different here. The requirement here is, in this branch and bound, as you can see, that once a node becomes active, or we can say it becomes alive, another node can become active only when the current node's all children have been generated. So this is how it differs from backtracking. We'll see the difference in more detail later. So one of the distinguishing characteristics of this branch and bound technique is that the children of the currently active node need to be generated, all the children to be precise, have to be generated before any other node becomes active. Now in this particular technique, it's also assumed that each answer node in the state space tree has some cost associated with it, and we have to find a solution, that is a path from the root of this state space tree to some leaf node, such that the total cost is either minimized or maximized depending upon what problem is at hand, whether the optimization problem is a minimization problem or it is a maximization problem. However, in this particular lecture we will be considering only the minimization problems, and it is obvious that any minimization it is obvious that any maximization problem can be converted into a minimization problem by negating its objective function. These things will be more clear as we move on. We need to remember that in a branch and bound solution there are 2 points. Number one, we have either to minimize or maximize our objective function, and second, while we are searching the state space tree for a solution, we need to consider the fact we have to generate all the children of the currently active node before any other node becomes active. This particular technique is mainly suitable for optimization problems, and as I said, that optimization problems can be minimization problems or maximization problems, but in this lecture we'll be dealing with minimization problems only, and this technique can be generalized to maximization problems as well by simply negating their objective function. So let's see what this generation of all the children means in this branch and bound solution. So if you remember, when we were discussing backtracking solutions, we followed the depth first search technique of searching the solution in the state space tree, the depth first mechanism. Let's recall that example of the 4 queens problem. As you can see, we have a root node and we have selected one of the possible nodes in our solution. So we have selected the first row and first column for this case here. Now the next node would be for the second particular row, and we'll have to select a column which would fit in our solution. So let's suppose the first column in the second row is not feasible, as you will be remembering how we generated this solution. However, the second one can be considered, and then it is evaluated whether it is feasible or not, and we find that obviously these are diagonally attacking queens, so this particular node has to be killed. Now you remember here that the earlier node that we considered was the first row, first column, and it was active. We generated one of its children and made that particular child as an active node. We have not generated all the children for this particular node, as you can see on the screen, but we have generated one child and made that particular child as active. This is how we did how we followed the backtracking procedure, but in branch and bound it will be different. So we'll follow this example. So we find that this node is not feasible, so we'll kill it, and parent becomes active and another child of this particular node is generated, and this child is now made active. Okay, we have again not, its parent has not yet been fully explored. Okay, and we are activating one of its childs, and we follow this scheme and so on and so forth till we kind of find our solution. Again, as you can see, another node is created, but its parent has yet not been completely explored. So this is not what we do in branch and bound. In branch and bound, this is again following the DFS, depth first search scheme in backtracking. But in branch and bound follows a breadth first strategy to find the solution in the state space tree. There are two ways of implementing the breadth first search solution. One is using a queue, which is also referred to as a FIFO scheme. So we are given the root, as you can see on the screen, we are given the root, and we generate 4 children corresponding to the 4 choices that we have for the first row. First queen placed in the first column for the first row, queen placed in the second column for the first row, and so on and so forth. So we generate all the children. Okay, once we have generated them, we add them to a queue, as you can see at the bottom right there. This is a queue we maintain, and we add all these children to a queue. Then from this queue we select another active node, or we activate one of the nodes from the queue. So this is obviously different from the backtracking solution where we follow a depth first search scheme. So this is a breadth first search scheme wherein a queue is used. So we take out children in the first in first out order. So obviously, as you can see in the queue, the node at the front end is 1. So we choose this one to be activated and generate all its children. Now once they are generated, they are added to the queue. As you can see here, they are again added to the queue, and so on and so forth. So the next node that would be active would be 2. So these nodes have been generated, 5, 6, 7, they have been added to the queue. Then node number 2 becomes active, and these 8, 9 and 10 number nodes are generated, and so on and so forth. So again they are added to the queue, and then node number 3 would become active. Now another scheme of implementing this breadth first search strategy would be using a stack. Okay, it's also known as a depth search. Okay, not the depth first search, but a depth search for implementing a breadth first search algorithm. So from the root we generate its children. Okay, these are the 4 children that we have generated, obviously maybe in order. First node number 1, then node number 2, then node number 3, then node number 4, but none of them has been activated yet. We add all these children to a stack. On the left side you can see this is a stack. So the first node that was generated would be at the bottom of the stack, then 2 would be inserted in the stack, and 3 and so on, 4th node would be added to the stack, and thus the stack would grow. Then the next node to become active would be taken from top of the stack. So node number 4 is taken in this case. So node number 4 would be expanded, all its children would be generated, and they would be again added to the stack in the order they were generated, okay, before anyone else is made active. So node number 5, 6 and 7 are added to the stack, and then node number 7 would be taken up. Okay. Now as you can see, if you follow the solution for this 4 queen problem, you will see node number 7 is not feasible, so it is killed right there. Then node number 6 is taken up, and so on and so forth. So these are the 2 techniques that we can use to search the state space tree for a branch and bound solution. So obviously both of them are basically breadth first search techniques. However, they are implemented in different ways. One uses a queue, another one uses a stack. So the first point for this branch and bound solution is clear. It generates all the children of the currently active node before any other node is made active. So we can follow that using a breadth first search strategy, implemented either using a FIFO or a LIFO strategy. Now the second point that needs to be considered here is that it is assumed that each answer node X in the state space tree has a cost C of X associated with it, and that the minimum cost answer node needs to be found. So in either case, whether a minimization problem or a maximization problem, the cost of a node at the cost at any particular node X at any level is equal to cost of reaching the current node X from the root plus the cost of reaching an answer node from that particular node X. So these 2 costs need to be added to get the final cost when following that path from through that node X. Now if it is the minimum cost as our objective is, then we'll consider this solution. If it is not, obviously then this is not a solution. So it means that this node does not belong to the solution path from root to the leaf node or the answer node. So the challenge here is, however, how do we estimate the cost of reaching an answer node from the node X? Actually, that is the problem that we need to solve. We cannot know it beforehand, what is the cost of reaching from a current node to the answer node, whether we should consider this current node X or not to be part of the solution or not. So this is where the problem basically lies, and we somehow need to find an approximation that helps us in making a decision whether the current node should be expanded or should be considered as part of the solution or not. So we will represent the first part of the cost as g of x, and the second part, which is the problem part, as h of x. So how do we do it? We basically use an estimate of the cost, and using an approximation cost function c cap of x, as you can see here. This is the representation of that particular approximation cost function. Now this approximation cost function has to be such that for any node x, okay, its value has to be less than or equal to the actual cost for that particular node. And the property of this cost function is that for an answer node, for the solution node or you can say the leaf node at the end of the tree, has this property that the approximate cost is equal to the actual cost for a solution node x. So this is how we will proceed about building a solution using a branch and bound technique. So the approximate part, as I said earlier, for this approximation cost function is h of x, which is basically the cost of reaching a solution node for x, and it is not known. So how do we kind of use this cost function, and how does it help us in bounding our search in the state space tree? So as I said earlier, the cost function is such that the approximate cost has to be less than or equal to the actual cost at that particular node. And this approximate cost function is used to provide the lower bounds on the solutions obtainable from any node x. Now we also use a notion of an upper bound on the cost of minimum cost solution. So if this upper is, let's suppose that an upper bound on the cost of a minimum cost solution, then all the live nodes, for example in our queue, let's suppose we are using a breadth first search solution, for any node x belonging to the list of active nodes, this approximate cost function, if it gives a value which is greater than the upper bound, so let's suppose we associate with each node a function which gives us an upper bound, and if the approximate cost function yields a value which is greater than that upper bound, again I need to remind you that we are considering the minimization problems. We are generalizing this branch and bound solution to minimization problems. So if this approximation function gives us a value which is greater than some upper bound, which in our case is considered to be the worst case. So if it gets worse and worse if we, for example, expand a particular node x, so there is no need of expanding that particular node x, thus we can simply kill that particular node, and all nodes which are reachable from x obviously will have this cost greater than or equal to the approximate cost function, which is greater than or equal to the upper, and we do not need larger values because we have generalized our problem to minimization problem. So how do we choose for these this lower bound and the upper bound? How do we compute them for a given particular problem? So the simplest choice for this approximate cost function and the upper bound functions are the objective functions of the problem itself. So we can modify the optimization problem that is given, and we can use them to build our upper bound and lower bound functions. This will be more clear when we discuss a specific example. Now let's consider our traditional 0 and knapsack problem. We have tried to solve it using backtracking. You have also solved a version of this knapsack problem using the greedy method. Okay. Now we'll try to find a solution to this 0 and knapsack problem using a branch and bound algorithm or a branch and bound technique. Again, the notion that we have earlier used, we consider this knapsack problem to be a maximization problem. As we can see, simply remind you that this knapsack problem is all about 0 knapsack problem. The given n positive profits associated with those weights, okay, and a positive number m, which is the size of the knapsack, the problem calls for choosing a subset of weights such that the total weight of the products or the items that we choose from our set is less than or equal to m, which is the knapsack size, and the profit is maximized. This is the total profit that we get from selecting x i's. So this is a maximization problem. But as I said, that the branch and bound solution that we'll be discussing in this lecture would be a minimization problem. So we can convert this maximization problem into a minimization problem by simply negating the objective function. So here you can see minus or negative of this total profit that we get needs to be minimized. So we can convert any particular maximization problem to a minimization problem. So that's what we will be doing here. So we have to solve the 0-1 knapsack problem using branch and bound, and the objective function is this, and it needs to be minimized here. Okay, the negative of this needs to be minimized. So how do we choose for the approximate cost function and the upper bound, such that the approximate cost function is less than or equal to the actual cost of that particular node x, which is less than or equal to the upper of that particular node x. So how do we do that? So let's take this scenario that we are searching at particular building our solution tree, and we are at a level j. So let's consider that we are dealing with a node x belonging to a level j. Now obviously the total number of levels would be n plus 1, because initial root does not represent any solution. So the solution starts from level number 2 to n plus 1, and where n is the total number of items that we have. So let's suppose we have this node x belonging to a level j, and we have already made assignments to all xi's less than j, or we have selected the nodes up to level j, and we can determine the profit that we have so far up to level j. And how do we do that? It is the cost of these assignments that we have made so far would be the product of whether we have chosen that particular node or not into that particular node's profit, and this is minimized, okay, so that it's minimized. And the weights of these assignments is similar to the earlier case, the weight of that particular item which we have selected. So xi would be 1 for an item which we have selected, and it would be 0 for an item which we have not selected. So these are the two values that we know before level j, okay, and these two quantities q and v are what we know so far. And how can we compute upper for it? Okay, so upper bound, it's similar to what we have done earlier. We use a function upper b which takes these values, this q and v value, and takes this level up to which we have found the solution and the size of the knapsack. Okay, I hope you remember this function. So this upper bound function takes the profit so far, the weight so far that is filled to the knapsack, the level up to which we have already found the solutions, and the weight of the knapsack. Now this portion, this piece of code basically fills the knapsack up to the level where no more items can be filled. But the point here is we are not taking fractions. So we keep on adding an item only if its weight is less than or equal to m. If adding an item to the knapsack, the total weight that we have added to the knapsack is more than the capacity of the knapsack, then that item won't be added. So we are not considering fractions here, we are considering whole items. Okay, so whether a whole item can be added to the knapsack, we'll consider it. If it cannot be added to the knapsack, then we will be leaving it out. So these additions are made for k plus 1 to n, that is for the remaining items which we have not yet been added to this knapsack. Okay, in this case up to level k we have already added, and we know the cost so far, the weight so far, and we find all those items that can be added to the knapsack such that the total weight is less than or equal to the size of the knapsack. So this particular function does not consider fractional parts of the items. So we can have specifying that tightest bound. Okay, so this is the tightest bound that you can have by filling in the remaining items into the knapsack. And this is generalized, the same algorithm is mentioned here. This would be the upper bound. Okay, how we calculate the upper bound for a node k. And for the approximate cost function, this c cap, we will use a variant of the similar function, but here we'll be using fractions. That is, we will be filling in the knapsack up to its capacity. Okay, so if there is an item which cannot be put into the knapsack as a whole, we will take only a fraction of it. So this would be the lower bound, since our problem is a minimization problem. So this function would give us the lower bound, and this function would give us the upper bound, and that is how we will be bounding the solution in the state space tree. So the final algorithm using a branch and bound strategy for solving the zero and knapsack problem would be something like this. It takes a node from where we are starting, okay, the level at which we are and the number of items that we have as input. Okay, this function is initially called by creating a new node. Now this node has these members, as you can see. Each node has a link to the parent. Each node has the approximate cost that has been calculated using the lower bound function. It has the actual cost, and it is the weight, how much it contributes after we add this particular item to the knapsack. And this x variable here, or the member of this node, it takes values either 1 or 0. 0 if this item is not added to the solution, and 1 if this particular item is added. So we'll see how this function runs. So we call this knapsack FIFO branch and bound function by sending this node here. This node is sent as the first, also the root node. Okay, so it does not have a parent. Approximate cost for this parent, this initial root node, is 0. The cost is 0, the weight is 0, and the solution value for this particular root node is also 0. That means this is not part of the solution. Okay, so we send level 1 and n. N is the number of items that we have. So we are at level number 1, 1 being the level for the root. If the k, that the level at which we are, is equal to n plus 1, means the last level that is possible, and the node that we have at hand right now, meaning the currently active node's approximate cost is equal to the actual cost, and we are at the last level, then we'll simply display the solution and the upper. How do we display the solution? We'll simply traverse the parent link of each node from the solution node up to the root and display the solution, and this upper value at that particular point of time would be the minimum possible cost. Now if it's not the solution node, for an intermediate node, so we see if the approximate cost for this particular node is less than upper. So obviously if this node is a possible solution node, in case its lower bound is less than or equal to the upper bound, then we generate its left child and the right child. In order to generate the left child, we'll see if the current node, we add this particular weight to the so far weight that we have in the knapsack, and if that weight is less than or equal to m, only then we'll generate this particular left child. And once it is generated, we'll generate this new node left. The cost is equal to the current cost plus, or since we won't be adding because it's a minimization problem, we are negating the final cost function, so minus the profit of for this particular node, and the weight is equal to the so far weight plus the weight of this particular node, and x for this particular left node is equal to 1, means we are considering this particular item. After we have done that, we test whether this left child needs to be saved in the queue or not. Same is done for the right hand child. So we generate the right child, compute its cost, compute the weight, okay, and the right child means that this particular node is not being considered, so x is equal to 0. For both cases, we call a function test. What this test function does, it validates the bounding. Okay, so we send the node, okay, and we send the level at which we are verifying or trying to bound. So we call the upper bound function for this current node, okay, save it to temp1, and we call the lower bound function for the same node and save it to node dot approximate cost, and then test the conditions. If the approximate cost is less than or equal to upper, then we enqueue this node, okay, add it to the queue, and similarly if the new upper bound is less than the earlier upper bound, see this temp1 stores the new upper bound, okay. So if this new upper bound is less than or equal to the so far upper bound, then we save this new bound into this variable upper. We'll see later how we use that. So these are the functions that we'll be using to find a solution. We have these upper bound, we have the lower bound, we have this this main parent function which keeps on calling the other functions, and finally this statement here removes a node from the front of the queue and makes it as the current node and recalls this function recursively and keeps on doing that. We'll try to dry run these set of functions on this example here So let's suppose on the top right corner, this is the problem state that we are given. So these are the weights associated with the various items, these are the profits, and we have the root node initially. The upper variable is initially set to infinity, okay, and the again here upper value is infinity, the approximate cost is 0 for the root node, okay, and obviously the parent would be null for this root node as well. So we try to generate the children of this particular node. So the first child will be node number 2 and the second child to be generated is node number 3. So for this node we compute its lower bound, okay, that means the best cost that can be obtained if we follow this particular node. So this is where we go. So if the best possible cost that we get if we consider this particular node is that we can have profit 10, then again 10, then this would be 32 in total, and some fraction of this particular node which will finally yield minus 38 to be the lower bound. And the upper bound would be only the first item, the second item, the third item, and this item won't be able to add this fourth item into this knapsack, because that would exceed the capacity of the knapsack. That is how we compute the upper bound. So only up to this portion we can add to the knapsack, that would give us the upper bound, which is equal to 32, okay. So for this node you can simply see how these two functions are called. So here we are calling lower bound, here we are calling upper bound for this particular node. Similarly for this node, it means we are not considering node number 1, okay. So the best possible cost that we can get would be the total cost here minus 2, and which is basically 32 in this case. Lower bound function which you will call for this particular node yields minus 32, and the upper bound function yields 27. Now we add these nodes to the queue on the bottom right side, if you can, as you can see, and we also save the lowest upper bound that we are getting. We are getting minus 32 to be the lowest upper bound, okay. Now we choose node number 2 from the queue. From this queue we choose node number 2 and expand it, generate its children. Again, this is the lower bound for this particular node. If we consider this is the upper bound, okay. Similarly for this node, this minus 36 is the lower bound and minus 22 is the upper bound. Now again we add these two to the queue here. So 4 and 5 are added to the queue. The next node to become active would be node number 3. So again for node number 3 we generate the 2 children, node number 6 and 7. For node number 6, minus 32 is the lower bound and minus 27 is the upper bound. Similarly for 7, minus 28 is the lower bound and minus 28 is the upper bound. Now for these two nodes, it is obvious that node number 7's lower bound is greater than upper, isn't it? Minus 28 is greater than minus 32. So we can simply kill this node number 7 right there and only add node number 6 to the queue, as we have done here. So the next node that can be expanded is node number 4, because it is at the front of the queue, as you can see. So we select node number 4 and generate its 2 children, which is node number 8 and 9. Again, the upper bound here for node number 8 is the lower bound is minus 38 and the upper bound is minus 32. Similarly for node number 9, the lower bound is minus 38, the upper bound is minus 38. So we add node number 8 and node number 9 to the queue, as you can see here. But we can also see that the new upper bound value, that is minus 38, is less than the earlier value of upper. Upper earlier was minus 32, but the new upper that you see here is minus 38 for a node. So we save this minus 38 in the upper variable here. So we take this node number 5 and we see that its approximate cost is greater than current upper, okay. So you can simply remove this particular node, okay. We can simply kill this. As soon as it is removed from the queue, we see that its approximate cost is greater than the current upper, which is 38, which we have just modified, and we can simply kill this node. So we have killed this node number 5. Now front of the queue is node number 6, so we'll be taking this out and try to expand it. Again, as you can see that approximate cost for this particular node, or the lower bound for this particular node, is greater than the current upper, which is minus 38. So we can also remove this particular node, or kill this particular node. So the next node in line is node number 8. Its left child cannot be created because that would exceed the capacity of the knapsack. So the left child is not generated for this particular node, node number 8, and the right child is considered. And as soon as we generate this right child, we see that its approximate cost is greater than the upper bound that we have, and it can be simply killed over there. So we are killing this node number 10. So the last node that is alive in the queue is node number 9. We take this out and generate its left and right child. So the left child is the lower bound and this is its upper bound. Similarly, for the right child, the lower bound is minus 20, which is way greater than the upper value that we have currently, which is 38. So node number 12 would simply be killed, and this node number 11 is our final solution. So this is how basically the branch and bound solution is found using a breadth first search strategy. Here we used a queue, so we followed a FIFO strategy for finding a solution, and it obviously generates lesser number of nodes than if we had gone through backtracking. Okay, if we compare the state space tree which is generated by following a backtracking algorithm, the number of nodes would be more. In this case, the FIFO branch and bound are relatively lesser. So this is it for today, and in the next class we will be discussing a variant of branch and bound algorithm which basically uses a least cost search to optimize the searching strategy. Till that class, it would be thank you. Goodbye.